In this video, I want to talk about quantum numbers. So let's say we have a chlorine atom. We know chlorine has 17 electrons. And we know first these electrons fill up the 1s orbital, and then these electrons fill up the 2s orbital and 2p orbital. And then we know the electrons will fill up the 3s orbital and 3p orbitals. However, something important to realize is each of these electrons can be characterized by a set of 4 quantum numbers. And these 4 quantum numbers are the principal quantum number, the azimuthal quantum number, the magnetic quantum number, and the spin quantum number. For example, this particular electron in this particular orbital can be characterized by these 4 quantum numbers. For example, this particular electron would have a principal quantum number of 3, an azimuthal quantum number of 1, a magnetic quantum number of -1, and a spin quantum number of +1/2. However, this particular electron in this particular orbital would be characterized by these 4 quantum numbers. And this particular electron in this particular orbital would be characterized by these 4 quantum numbers. So again, every single electron can be characterized by these 4 quantum numbers. However, why does this particular electron in this particular orbital have a principal quantum number of 3 and an azimuthal of 1 and magnetic -1 and spin +1/2? Well, to understand this, let's do an example. Let's find the 4 quantum numbers of this particular electron in this particular orbital. So to determine the principal quantum number, we just need to know the number of the orbital. For example, we have 1 orbitals, we have 2 orbitals, and we have 3 orbitals. So we see this particular electron is in the 3p orbital, so therefore the principal quantum number of this particular electron is 3. And what's important to realize, this principal quantum number tells us the size and the energy of that particular orbital. And the larger the principal quantum number, the more energy there is in that particular electron orbital. But again, we see this particular electron is in the 3p orbital, so therefore this particular electron has a principal quantum number of 3. And something important to realize are the possible values of principal quantum numbers are just any integer. So as long as your principal quantum number is an integer, you know this is a feasible quantum number. So what about the azimuthal quantum number of this particular electron? Well, we know there are s orbitals, we know there are p orbitals, d orbitals, and f orbitals. And we know these orbitals have different shapes. For example, all of these s orbitals have a spherical shape. And we know p orbitals have this lobe shape. But something you simply have to just memorize is that whenever you have an s orbital, the azimuthal quantum number is 0. Whenever you have a p orbital, the azimuthal quantum number is 1. When you have a d orbital, the azimuthal quantum number is 2. And when you have an f orbital, the azimuthal quantum number is 3. And this is something you just simply have to memorize. But we see this particular electron is in a p orbital. So we know whenever we have a p orbital, the azimuthal quantum number is 1. So because this electron is in a p orbital, we know this electron has an azimuthal quantum number of 1. And we can see this particular electron is in an s orbital, so it would have an azimuthal quantum number of 0, because we know whenever we have an s orbital, the azimuthal quantum number is 0. So this is simply something you just have to memorize. But now we can see why this electron has an azimuthal quantum number of 1. And something you just need to know is that the possible values of azimuthal quantum numbers are 0 all the way to n-1. So we see this particular electron, we know it has an n of 3. We already determined that. So we know n-1 is 3 minus 1, which is simply 2. So now we know the possible values of an azimuthal quantum number are 0 all the way to n-1, which is 2. And we see our azimuthal quantum number we determined was 1. And we see that's feasible. 1 falls under 0 to 2. So we see this is a feasible azimuthal quantum number. So we know with confidence this is probably the right answer. So how do we determine the magnetic quantum number of this particular electron? Well, something you just need to memorize is that the center orbitals will always have a magnetic quantum number of 0. Then the adjacent orbitals will be -1 and +1. So with this 3p orbital, we see the center orbital would have a magnetic quantum number of 0, and this orbital would have a magnetic quantum number of -1. And this orbital will have a magnetic quantum number of +1. But we see this particular electron falls under this orbital, so therefore we know this electron would have a magnetic quantum number of -1. And hopefully you can see the pattern. It's pretty straightforward. For example, this 2p orbital, this orbital has a magnetic quantum number of 0, and then on the adjacent orbitals we have -1 and +1. And for these s orbitals, we only have one orbital, so the magnetic quantum number is 0. And to help see the pattern, let's look at iron. Iron would have magnetic quantum numbers that look like this. For example, this 3p orbital, the center orbital is 0, then the adjacent orbitals are -1 and +1. And when it comes to this d orbital, again, the center orbital has a magnetic quantum number of 0, then the adjacent orbitals are -1 and +1, and then those adjacent orbitals are -2 and +2. So hopefully you can see the pattern and see it's really pretty straightforward. So again, this particular electron is in an orbital with a magnetic quantum number of -1. So therefore this particular electron has a magnetic quantum number of -1. And what are the possible values of a magnetic quantum number? Well, they range from -L to +L, where this L represents the azimuthal quantum number. So remember, this particular electron has an azimuthal quantum number of 1. So therefore, the possible values of a magnetic quantum number range from -1 to +1. Because again, remember, this L represents the azimuthal quantum number. And we see our magnetic quantum number is -1, which falls under this range. So we see this is a feasible magnetic quantum number. So what is the spin quantum number of this particular electron? Well, something important to realize is each orbital has 2 electrons. And one electron will always have a spin quantum number of +1/2, and the other electron will have a spin quantum number of -1/2. And that will be true for any orbital. Each orbital holds 2 electrons. One will have a spin quantum number of +1/2. The other will have a spin quantum number of -1/2. So again, this particular orbital has 2 electrons, and this particular electron we're interested in, we see has a spin quantum number of +1/2. So now we know this electron has a spin quantum number of +1/2. So these spin quantum numbers are pretty straightforward. And in terms of the possible values will either be +1/2 or it will be -1/2. Those are the only 2 possible values. So again, we see our particular electron happen to have a spin quantum number of +1/2. So now we know how to determine the 4 quantum numbers. And this particular electron, we know we can characterize by these 4 quantum numbers. And again, this particular electron has a principal quantum number of 3, which just tells us about the energy of that particular electron in that particular orbital. And we know this particular electron has an azimuthal quantum number of 1. And we know this azimuthal quantum number tells us about the shape of the orbital. And again, an azimuthal quantum number 1 is a p orbital, and we already explained the rules for that. And we know this particular electron has a magnetic quantum number of -1. We already explained how to determine that. And we know it has a spin quantum number of +1/2. So let's try another example. What about this particular electron in this particular orbital, this 2p orbital? Well, again, we know every electron can be characterized by these 4 quantum numbers. So what is the principal quantum number of this particular electron? Well, we know we just need to determine the orbital number. We have 1 orbitals, we have 2 orbitals, and 3 orbitals. So again, this particular electron is in a 2p orbital, so therefore this particular electron has a principal quantum number of 2. However, what is its azimuthal quantum number? Well, remember, something you just need to memorize is whenever it's an s orbital, it has an azimuthal quantum number of 0. When it's in a p orbital, it has an azimuthal quantum number of 1. D orbital, it's 2. F orbital, it's 3. So again, we see this particular electron is in a p orbital. And again, you just need to memorize. Whenever you have a p orbital, the azimuthal quantum number is 1. These are just rules you need to memorize. So therefore, because this electron is in a p orbital, its azimuthal quantum number is 1. So what is this electron's magnetic quantum number? Well, again, remember this pattern. The center orbital has a magnetic quantum number of 0, then the adjacent orbitals are -1 and +1. So we see this electron is in this particular orbital, so therefore it has a magnetic quantum number of +1. So what about the spin quantum number of this particular electron? Well, again, remember each orbital has 2 electrons, and one electron will have a spin quantum number of +1/2, and the other electron will have a spin quantum number of -1/2. So again, this particular electron would have a spin quantum number of -1/2. So now we know the spin quantum number of this particular electron. So now we've determined the 4 quantum numbers of this particular electron. So let's try another example. Let's say we have iron. What are the 4 quantum numbers of this particular electron? Well, we know the principal quantum number is just the orbital number. So again, we have 1 orbitals, 2 orbitals, 3 orbitals, and 4 orbitals. But again, this particular electron is in the 3d orbital, so therefore this particular electron has a principal quantum number of 3. So what about the azimuthal quantum number? Well, again, remember, you just have to simply memorize these rules, where the s orbital has an azimuthal quantum number of 0, the p orbital has a number of 1, d orbital 2, and f orbital 3. So again, we can see this particular electron is in a d orbital. So therefore, the azimuthal quantum number of this particular electron is 2, because again, whenever you have a d orbital, the azimuthal quantum number is 2. So again, we're in a d orbital, so the azimuthal quantum number is 2. What about the magnetic quantum number? Well, again, remember this simple rule. The center orbital has a magnetic quantum number of 0, then the adjacent orbitals are -1 and +1, then those adjacent orbitals are -2 and +2. So again, we see this electron falls in an orbital with a magnetic quantum number of +1, so therefore we know this electron has a magnetic quantum number of +1. And again, with spin quantum numbers, remember each orbital is capable of holding 2 electrons, where one electron will have a spin quantum number of +1/2, and the other electron will have a spin quantum number of -1/2. So again, we see this particular electron would be designated the +1/2 spin quantum number. So therefore, this electron has a spin quantum number of +1/2. So again, the point is, when it comes to any electron, you can choose any random electron. For example, let's focus on this particular electron. We can characterize this particular electron in this particular orbital with these 4 quantum numbers: the principal quantum number, the azimuthal quantum number, the magnetic quantum number, and spin quantum number. And we learned how to determine those quantum numbers. So hopefully now you understand the concept behind these quantum numbers and these electron configurations.